Okay.
Chat is currently open. Well, first of all, welcome everyone to this Princeton Area Alumni Association, or PA3 event. We have a distinguished guest with us tonight to talk about a fascinating subject. So thank you very much, Matt, for spending an evening with us. But before we get to him, before we introduce Matt, some housekeeping. First of all, this session tonight is going to be recorded. Chat is currently open, so if you want to chat with anybody on the call, you can do that now using the chat function. However, once our presentation starts, chat will be only available to ask questions. And the way you do that is you'll go into chat and you will select me and you'll send your question to me. And then when Matt is done with his presentation, I will put him to the question, not the way the English kings used to put him to the question. I will put the questions to him. And I also asked that, well, I think you're all going to stay muted according to Mo. But if something goes wrong and you do find yourself unmuted, please mute yourself so that we don't have any distracting background information. So with that, I want to tell you a little bit about upcoming events for PA3. But before I do that, I want to thank George Buston very much for arranging to have Matt join us tonight. And I want to thank Mo, our vice president, who just puts a great deal of effort into the logistics to make sure that these events work smoothly and I don't screw something up. So thank you, George. Thank you, Mo. Now what I'd like to do is just tell you a little bit about what's coming up in the next month in terms of PA3 events. On Saturday night, we're going to have our sixth virtual wine tasting. And this will be German whites and Austrian reds. So if you haven't been to one of these, please try it. The wines are available at Public Wines in Princeton. There's a matching cheese selection that's available from, I forget the name of the place, but it's also in Princeton. And these are really a lot of fun. And we will eventually do them non-virtually or in a hybrid fashion. Next Tuesday, we have one of our famous propeller series on technical innovation. And this one has to do with transforming medical logistics through the use of drones. Interesting topic. On the 19th, you're all invited to participate in the ceremony where the Princeton Prize in Race Relations is going to be awarded to the local winner. And that's always that's a very worthwhile thing. And then lastly, on May 27th, we have our book club. So that's what's coming up in May, and I hope you join us for as many of those events as you can. And with that, I'm now going to turn the mic over to George Buston, who is going to introduce our speaker. George.
Thank you, Tom. I have the pleasure to introduce my friend and quasi-classmate, Matt Miller. He's a quasi-classmate because he's married to one of our most distinguished classmates, May Wong Miller, one of the first 9 women to receive an undergraduate degree from Princeton. Matt has worked in the technology industry for more than 40 years. He's been a bench scientist, a high-tech project manager, serial technology entrepreneur and CEO. He's contributed to numerous fields, including space-based instrumentation, atmospheric photochemistry, semiconductor devices, and digital communications. He played a major role in the development, standardization, and practical deployment of US HDTV and high-speed cable modems. Matt has also consulted extensively in both private equity and venture capital communities, has served on numerous boards of directors, in addition to having served on investor advisory boards. He is now the president and co-founder of the Stellar Energy Foundation, Inc., a New Jersey nonprofit corporation formed in 2016, with the mission of accelerating the development and deployment of fusion energy as a component of the net zero power portfolio. And he is currently serving as a consultant to the Princeton Plasma Physics Laboratory. Matt holds a bachelor's degree in physics from Harvard, 1968. And as we discovered just before we opened, he also seemed to have majored in English at some point. And perhaps more to the point this evening, he has a PhD in physics from Princeton in 1974. Matt has spoken to several different Princeton forums over the last few months, including my own class, Midwinter Dinner, and the Chicago Area Princeton Alumni Association. He's in demand, and we are really very lucky to have him with us tonight to give us an explanation of fusion without tears. Thank you, and Matt, over to you.
George, you are really good. So what I'd like to say is I'd like to thank you all for giving me a chance to talk to you. I'd especially like to thank, and I hope I don't leave anybody out, but all my good friends in the class of 1970, Bruce Millman, Mickey Pohl, George Buston, Bill Neidig. You guys you're a wonderful group of people, and it's been a great pleasure for me over about a 50-year period to be your brother-in-law. Probably the best thing that ever happened to me in my life, as you well know, is having the good fortune to meet, fall in love with, and marry one of your classmates, May Wong, now Miller. It's good to make at least one good decision per lifetime, and that was a good one. So guys, thank you very, very much. It's just a real treat to be associated with all of you. So that said, the topic here is Princeton Plasma Physics Lab, not your father's Plasma Physics Lab, and kind of fusion in the future. Many of us were around in the class of 70 as plasma physics was just beginning to start getting some global popularization. It's had its ebbs and flows. And it is a really important component of a path forward to a zero carbon future. So with that, Mo, next slide, please. I got involved in the plasma physics environment in 2016. I am a founder and president of the Stellar Energy Foundation. We were founded in 2016 with the mission of bringing fusion to the zero carbon grid soon enough to have an impact on climate change. We have dual activities. We have a communications activity and advocacy where we try to broaden the reach, depth, and understanding beyond the traditional fusion community of what this important technology can be. And in addition, we do provide targeted technology support. We are very pleased that we recently executed possibly the first ever three-cornered billiard shot of a public, private, and philanthropic partnership to try to advance some really exciting new technology involving a private company and the Princeton Plasma Physics Lab. On the advocacy side, 2 years ago, we hosted an in-person significant meeting roadmap to the fusion economy. We had about more than 100 people from all around the world. This January, we hosted a webinar, Energy, Environment, and Innovation, Fusion's Promise for Our Climate. We had over 400 people at that, and luckily for us, one of the attendees was George Buston, and he found the topic sufficiently interesting to try to help me spread the word among others. We are planning another webinar in mid-June, focusing on private sector, on mobilizing the investment community into fusion. And we had the good fortune, literally as of this morning, of being invited to host a session at the upcoming International Atomic Energy Association Fusion Conference. They only hold these once every 2 years. And we're going to have an invited session there where we're going to do a rerun of the January webinar with an extended Q&A with an all-star panel of experts. Next slide, please. I have, I think, halfway decent presentation skills, but absolutely no presentation preparation skills. So I've relied on a number of very, very capable people embedded within the fusion community worldwide to help me assemble both the slides and to validate the themes of this presentation. And you can see here folks from private companies, from ITER, which is a global consortium, from the Princeton Plasma Physics Lab, from the investment community. I've had the good fortune of having access to the best minds in the area, and also among the friendliest people you'll ever meet. Next slide, please. There are a couple of takeaways here. Number one, human impact on climate is real. It's a major threat, but it's also a significant opportunity. As we move worldwide to finding economic and social solutions to the issues that surround zero carbon, a lot of good things are going to happen. So the response to the threat, if we don't respond to it, will be severe, but I think we will, and there are all kinds of great opportunities. I am not going to comment on stuff about which I know nothing. I know more than nothing about fusion, and I would like to discuss with you the role that fusion can play in the portfolio of solutions here. And very importantly for Princeton alumni, the Princeton labs have historically been a global resource for research into plasma physics and fusion generally. And as the world seeks solutions going forward, I think the labs will be a significant player in moving the ball forward on that. Next slide, please. The problem is obvious. I'm sure you've all seen this slide in one form or another, but essentially we are currently pumping out worldwide the equivalent of 51 gigatons a year of carbon dioxide as a greenhouse gas. If we don't do something about this, very bad things will happen to the climate. And there's the current policy approach, which can lead to a century-end temperature increase as high as 3.5 or more degrees centigrade. If we follow the Paris pledges, we may take that lower. There's a lot of talk lately. This presentation is actually 90 days old, and literally in the past 90 days, there has been huge attention given to the threat and the opportunity that greenhouse gas represents for us. And there are two approaches there that both need to be followed. One is emit less, and the other is try to extract more. I can't comment meaningfully on CO2 extraction, but I do have a word or two to say about heading for zero emission. Next slide, please. But very importantly, one thing that has changed in the fusion and energy space is that where a lot of this was viewed as a science project or an interesting thing for the future, or perhaps something that do-gooders could think about doing. There's a real business here. The global energy market is a multi-trillion-dollar market. And over time, as the market externalities force producers to find other ways than burning fossil fuel, there is an enormous opportunity for clean, economic, efficient means of producing energy at scale. And that's a very important concept, at scale. It is easy to come up with small solutions to produce small amounts of power, but running a growing global industrial economy requires major changes in the energy production and distribution infrastructure. Next slide, please. So fusion. Fusion really is nuclear physics. It's the easy nuclear physics. It's the process that basically runs the universe. It's the source of energy in the stars. It's the reason why we call ourselves the Stellar Energy Foundation. If it can be brought to Earth, it can really bring about genuine change, safe, clean, and essentially unlimited source of energy. It has been viewed as the Holy Grail for a long time. Certainly early years in the late 60s and early 70s, perhaps it was overpromising. There has been a kind of a fallow period, and that was part of the reason why we formed our foundation, was to try to inject some momentum into what we viewed as an essential component. And there's a lot of things happening these days that make us believe that fusion can happen. Next slide, please. Here's your one nuclear physics slide. Fusion is a nuclear process. I think most of us are familiar with fission, which is the process that makes old-fashioned atom bombs work, and which is also in current functioning nuclear reactors. In fission, you have a heavy nucleus, a neutron collides with it, the nucleus breaks up into two fission byproducts and emits some energy because the mass of the neutrons and the byproducts is less than the mass you started with. Einstein tells us E equals mc squared, and it's a source of a large amount of energy. The good news is it works. It's actually essentially a carbon-free source of energy production. You can turn it on and off. It's highly dispatchable. It's very high energy density. You don't need a lot of land to produce a lot of energy. And it probably could, in fact, produce enough energy to meet the world's demands. Fusion is a different nuclear process. It's the exact opposite of fission. In fusion, you take two isotopes of hydrogen typically. There are multiple fuel cycles, but the one that's most often looked at is the deuterium-tritium. I apologize for being technical. So it's heavy hydrogen and heavier hydrogen. You whack them together, you get a helium nucleus plus some energy. Like fission, it's very efficient, very dense, dispatchable. Unlike fission, it does not have any long-lived radioactive wastes, so the problem of toxic waste disposal is greatly reduced. It has essentially no nuclear weapons proliferation concern. The byproducts of fission can be turned into weapons. The byproducts of fusion cannot. And the fuel is really, really abundant. You don't have fuel scarcity. So if you could make fusion work, you would have all the advantages of nuclear fission. Very, very efficient, basically a universal source of power. It's inherently safe, and it's inherently zero carbon at a scale that could actually run the planet. So the question is, why hasn't this happened? And the answer is, it's been hard. Next slide, please. So the question of why would we want to pursue fusion? It's inherently safe, it's scalable, and it's essentially unlimited. It's zero carbon. It is in one man's view, the only clean energy solution that's got suitable density to supply the world's supply of energy if you don't use nuclear fission. And it can be a complement to other renewable sources. Very importantly, we do not view the path to zero carbon as a zero-sum game. There are so many possible ways to power the planet. We feel it would be a big mistake to pursue one path too few. Better to go down one road too many than one too few. There's wind, there's sun, there's nuclear, there's land mass use. You've really got to do it all. But fusion fits in that mix as an inherently safe nuclear source of power. Next slide, please. So the question is, why now? People have been banging away at this problem for 50 years. Fusion was first envisioned as a civilian source of energy back in 1958 when Lyman Spitzer started working at the Princeton Plasma Physics Labs, and I will get into that in some detail. But what has happened is that the goals for achieving net zero 2050 has really created a market externality that demands copious production of zero carbon electricity. So even though it is almost impossible without putting some kind of a price on carbon to compete on pure economics with a combined cycle natural gas electric generation system, it is the expectation that over time, the more expensive green options will be made economically competitive, either by some process of pricing on carbon or incentives on the distribution. So now there is a real economic reason to produce not small amounts of electricity, but enormous amounts of electricity in net zero. Since I last gave this presentation, Bill Gates has been on the road a little bit, and I would really recommend Gates's book. It's written in English. It's a little bit chatty, maybe not as formal as a professional scientist would like. It's kind of conversational. It's at a level that could be readily understood by an intelligent high school senior. But he gets all the essentials right. And he doesn't oversimplify. He doesn't leave a lot out. It's well organized, and it's backed up by a lot of data. A very important takeaway from the Gates book is that, and from the world in general, is that if you are in fact going to head for net zero, you are going to need to electrify many processes that currently do not use electricity. And that's very important. The total US electricity demand is going to go up 2.5 or 3 times. So that means that not only do you have to find a way to replace the current fossil fuel production of power, which in the US is a capacity of about 1 terawatt, you're going to have to double or triple that. And the challenge of doing that with the net zero sources of which we are familiar is going to be very difficult. So there's real market pressure to find a way to make a lot of electricity in an economic way without emitting carbon. That's new. Next, and I come out of the semiconductor business. The real advances in the semiconductor business were based on computation and simulation and materials and manufacturing methods. Intel could not put 1 billion transistors on a chip if they couldn't simulate that chip before they made it, and they couldn't make that chip if they didn't have very nearly perfect silicon materials to begin with. Similarly, in the area of magnetic confinement fusion in particular, and the way in which we produce the temperatures and pressures necessary to get nuclear reactions, typically large magnetic fields are required. And there have been enormous advances in magnetic materials, high temperature superconductors and permanent magnets. The computation and simulations capabilities, as we all know, are enormous. So now we can simulate these very complicated nuclear reactions without having to build the reactor and see what happened. And finally, with the development of additive manufacturing, 3D printing, it's possible to start producing structures that are entirely unimaginable as recently as 10 years ago. What else? The private sector engagement in fusion space is enormous. So there are now probably 20 different companies trying to develop approaches for commercial fusion, whereas 10 years ago, there might have been one or two. And very importantly, within the public sector, there has been a policy shift towards commercialization. Historically, most of the fusion energy research in the United States has been funded by the Department of Energy through the national labs, and the national labs had a very specific science-only charter. That is changing. There is now a viewpoint within the DOE and the national labs to look for public-private partnerships and to find ways to use the labs to supplement and augment the private sector to try to develop commercial applications. The timeline to practical deployment is much shorter. And I know we've all heard this joke, fusion is the energy source of the future and it always will be. The answer is things happen a lot faster now than they used to. And the public perception is just wrong. And one of our missions actually in our foundation is to try to bring together folks from outside the fusion community to understand why there is real reason to believe that this can happen. And finally, you really need, and this is technical terms, firm means it's there all the time, dense means it doesn't take up a lot of real estate. We need to have a firm, dense energy supply if we're going to meet the needs of a growing industrial global economy. And Gates, again, there are only three different paths where you need a miracle. You either need a miracle in storage, because you're going to need batteries big enough to run Manhattan. You're going to move forward with nuclear fission, which quite frankly, I think we should be doing, but there seems to be a social license opposing it. Or you can move forward with fusion, because that's the only way to get enough energy where you need it, when you need it, to run our economy. Next slide, please. So let's talk about Princeton's role in all this, because Princeton has really been central to plasma physics and fusion since there was such a discipline. Fusion, as I said, was originally primarily a military application. It's what runs hydrogen bombs. There was a very active weapons group actually at Princeton. And Lyman Spitzer, who was one of the smartest people who ever lived, developed a concept for a contained fusion reactor called what he called a stellarator, and began work with John Wheeler out in a rabbit hutch out in what's now the Princeton Plasma Physics Lab back in 1958. Next slide, please. So the Plasma Physics Lab has grown from a rabbit hutch in 1958. This is an aerial photo Steve Cowley shared with me. Steve is the current lab director there. He's an amazing guy. Sir Stephen, he led the UK AEA for a number of years. He led major projects in fusion in Europe. He's actually a Princeton PhD and came back here almost 2 years ago to revitalize and bring forward into the really active century the Princeton Plasma Physics Lab. The next slide, please. So now the lab has about 600 people in it. It's actually a DOE national lab. It's truly a national and a global resource. It's the only national lab dedicated exclusively to fusion. It is actually operated under a contract with Princeton University. So technically the folks who work at the labs are Princeton University employees. There are associated faculties there. Under Steve's guidance, there really has been an effort to grow and exploit more closely the relationship to the university and the university astrophysics department. If you look at this, the 19 budget was 140 million. I think it's probably up around 160 or 170 million now. 95% of the work that was done out there was fusion. They're actually trying to expand now into other plasma physics applications, but it is still primarily fusion oriented. Next slide, please. So the lab has 3 missions. By far, number 1 is to figure out a way to make fusion work. There have been recent policy changes, again, within DOE, where there is now an emphasis on trying to build a functioning pilot plant that is actually make electricity, as opposed to just PhD theses and students. In addition to that, the core technology for semiconductor and nanoscale facilities is plasma physics based, and the labs is building their capability there. And finally, there are other applications of plasma physics. I was commenting earlier in the day with Tom Swift. I said, this isn't really that complicated. It's not nuclear physics. Oh yeah, maybe it is. And then I said, maybe it's not that complicated. It's not rocket science. Well, maybe it is. It turns out one of the very promising non-energy applications of fusion could be for compact propulsion devices for interplanetary missions, that people are now looking at small compact fusion reactors to be used as rocket engines in space. Ain't gonna happen on Earth anytime soon. Next slide, please. So one of the things that we want to do, and by we, I mean the United States generally and the Plasma Physics Lab in particular, is to actually make a fusion pilot plant. So there have been a number of national studies recently, and there is a commitment now to try to actually make something within the next 5 to 10 years that will actually produce electricity, get more energy out than goes into it. That has not been done before. This is a major change in national priorities. Next slide, please. In addition to that, the why fusion now, if you read the daily press, there's been a lot going on. There have been, not just in the United States, but internationally, real momentum gathering in both the public and the private sectors of putting energy, attention, and competence into advancing this technology, because the time really has come. Next slide, please. So on the commercialization side, there are really 3 components driving the private fusion market. One is that people have really, really resolved many of the outstanding physics problems relating to physics plasma, magnetically confined plasmas. In addition to that, as I said, the enabling technologies, digital controls, high temperature superconductors, advanced manufacturing, you can start making systems that were literally unimaginable as recently as 5 years ago. And finally, there really is a fundamental economic and market-driven reason for doing this, which did not exist 10 years ago. Next slide, please. So this is a slide I borrowed from my friends at General Fusion. It's actually somewhat out of date, but if you look at it, you can see that where there were only a few private ventures, there are now probably 20. There's been probably $1.5 billion to $2 billion of venture capital put in. General Fusion just raised some new money. Commonwealth Fusion Systems just raised some new money. TAE just raised some new money. So the the private investment market is starting to look a little bit like what biotech looked like in the late 70s, when people were first developing the capabilities of using genetic bases to create pharmaceuticals, because a whole bunch of characteristics came together at the same time. We see a similar trend here. It's not just in the United States, it's worldwide. There's enabling technology, there's a market driver, there's real money on this that's seeking long-term investment in it, and there's a genuine market requirement. Next slide, please. There's even an industry association. Andrew Holland, who is the president of the Fusion Industry Association, literally created his association to represent the US private sector 2 years ago. He's now managed to put together an association with more than 20 members worldwide. They have a real voice. They're real. Next slide, please. These are a collection of names with which I would guess none of you are familiar. At least one of these is going to be a multi-billion-dollar company. I suspect more of them will be, because they're the guys that are going to crack the code for inherently safe, ubiquitous, zero carbon energy at a scale that will run the planet. So the question is when? The next slide, please. This is an excerpt from a report that Chris Gadomski wrote for Bloomberg New Energy Finance. Nobody really knows when, but the answer is sooner than you think. And with that, I'd like to conclude the formal presentation and open the floor for questions. Thanks very much.
Okay, Matt, thank you. We do have some questions. And again, I remind the audience that if you'd like to submit a question, just send a chat note to me. Several people have commented that 50 years ago, you told us that we were 50 years away from fusion. And now when we ask, when are we going to get this? We don't get 50 years, but we get, it's kind of a mushy answer. Now, I remember being on a tour of PPL, and that question was put to the director, or the tour director, sorry, and his response was, well, 50 years ago, if you gave us the money we asked for, we would have done it by now. So I'm wondering what your view of that is. Could this have been solved with a lot more money earlier?
So,
or was it simply we were trying to cook it too early?
so the last person who asked that question fell asleep before I was done with the answer, and it really is the right question. And I'm going to answer it in 3 parts, and I'm also going to pose one question for myself, right? The real question is, why does everything take so long and cost so much? And part of that is, when are we actually going to see something? So yes, Tom, it is true that as a nation, we systematically, first we overinvested. We overinvested early because there was a lot that we didn't know that we found out. Then we systematically underinvested for about a period of 20 years. And the way to spend a lot of money and never get anything is to spend a little money for a long time. So that is true. But it is also true that the technology really wasn't there. And the real advances, as I said, there are 3 things here. One is, this really is complicated physics, okay? In order to get a controlled fusion reaction, you need to confine deuterium and tritium at a near atmospheric pressure at 100 million degrees centigrade. That is not a simple thing to do. The harder you push on it, the more it wants to leak out. And there was an enormous amount of unrecognized difficulty in the physics. That's behind us now. People really do understand the physics, and they have the computational tools to go further. So that's reason for confidence. My personal view is that the timeline to development does depend on investment. I think realistically, to get a commercial power plant is going to be not less than 15 years. It'll be more if people don't invest in it. I don't know what you can do to pull it in because it's just a pile of work that needs to be done. But 15 years means kind of 2035-ish, okay? The target, if this is going to be meaningful, the power companies, the utilities are going to have to be able to plan on purchasing multiple hundreds of megawatts to gigawatts of generating capacity, and they need to know that it's going to be there by 2040. I think it can happen. I think there's reason to believe that it will happen, but it is by no means a certainty. I really don't want to oversell this. The fact that there is work being done worldwide and that there are a lot of smart people outside the US putting a lot of money into this right now. So now I'm going to go off into the global competitiveness question. Right now, I'd say China has a better chance of having nuclear fusion commercially than we will, because they can mobilize the resources. Why does everything cost so much and take so long? It's a question of urgency and priority. The national fusion research budget funded by DOE is still under $1 billion a year. And yet we spend $17 billion on one nuclear aircraft carrier. So I would say you could see a pilot plant in 10 years and real plants in 15, but only if people take it seriously.
Okay. I want to ask you about is turbulence a problem? Because turbulence has been a devilish problem for a long time. And I think there was a period of about 20 years where the fluid dynamicists really went nowhere because they didn't have the computers to try to solve the equations. And that's still a problem. Was that one of the issues?
Yeah, absolutely. The magnetohydrodynamics, and my apologies to those who continued to be English majors. It's really tough. There was a period, and you're right, Tom, there was a period where every time people built a machine, when they turned it on, they would find one more instability that they hadn't thought of, and there was nothing they could do to change it. The physics is vastly better understood now, and the simulations are vastly better. So if you take a look at the current generation of machines, and there's been real advances made outside the US. There's a gigantic stellarator built in Germany, the Wendelstein, WX7 machine. You don't need to know what it is. It's a miracle of German design and engineering. The goddamn thing worked as soon as they turned it on. Most complicated machine ever built. And it works. It does exactly what they said it was going to do. So there's reason to believe. There's a big machine now running in Korea, which is setting some world records. The biggest machine, of course, is ITER, the International Thermonuclear Experimental Reactor. This is, I think, the world's biggest construction project. It's a $50 billion program building a monstrous machine in the south of France. It was a little bit off track. They got themselves a new director general, and now marvelous things are happening there. So the long answer to the short question is, you're absolutely correct. There was a period of time when the physics was not understood, and the only way to understand it was to turn on an expensive machine, and then scratch your head wondering what went wrong. And that is no longer the case.
You mentioned there was a two-part question here. What temperature do you have to reach? You said that 100 million degrees C. And the second part of the question is, how many companies or I may say, how many labs have managed to achieve that?
None. That's an easy one. Nobody's gotten there yet. To get the objective here is to get what's called a burning plasma. Okay, so you can get it hot enough to produce neutrons, but what you really want to do is you want to get it hot enough to be self-heating. And I don't want to go off on a little bit of the physics conversation. There's a thing called the Lawson criterion, which is the product of temperature, pressure, and time. That's the magic number. You want to have stuff hot enough, dense enough, long enough to get more energy out than you put into it. And the Lawson products are getting near the place where you can have a self-sustained reaction, but no one's gotten there yet.
Okay, so we have these gigantic government led or funded projects, and then we have a proliferation of private companies that appear to be focused on doing this smaller scale, but you still have to create the reaction. Can you talk about is this a different vision? Is this a competitive horse race between the titanic efforts and a bunch of really sharp guys in a trailer somewhere? And there's a corollary to that, which is also, if you think about the electric grid, are we better off with a small number of gigantic power plants that then you have to have big distribution systems? And, I don't want those things going through my backyard. Or are we better off with a large number of smaller plants? So two parts.
So this session could go on for a long time because you're asking the absolutely correct questions. Let's go to public, private, big, small. What makes the little guys think they can accomplish something that the big guys haven't? And the answer is everybody has a little edge. The smaller companies are certainly more agile. All right, I've run a couple of startups, okay? And the productivity and the agility and the focus and the energy and the attention in a small company is just, you can't do that in the big institutions. On the other hand, this is a big problem. And I think eventually you're going to need to have cooperation, that the government and the big companies will do what they do best, which is the really big engineering, the really the move this out at scale. But the small companies can innovate. It's kind of the SpaceX model, right? Build, break, test, do it again. But SpaceX had multiple billions of dollars of US government money helping them along. And I think what the industry really is looking for is something like the COTS model, what NASA went through to develop a transportation system, which was to have the little companies do what they do best and to have the company and the government and the big companies do what they do best. So it's not so, now it feels, some of the small companies feel competitive because there are limited human resources, right? If you have all the smart people on the planet working in 2 or 3 big labs, because that's the whole fusion population, then little companies have a tough time recruiting folks. So there is a little bit of a competition there, but I think they're going to come together. There was another part to your question, though, that I kind of steamrolled over. Oh, the size of the production plants. I have a viewpoint, which is that a large central power generating facility is going to be a whole lot easier to drop into our current grid than a large number of small and distributed sources. And one of the reasons why I am enthusiastic about fusion is that once you're done with the fusion island, okay, you've got this DT generating heat, all right? The heat boils water, and after that, all the rest of it just looks like a plain old-fashioned power plant, right? Basically, these fancy fusion reactors are really just boilers. You make steam, you run a generator, and you could literally drop these things in where you currently have coal and natural gas and use the existing distribution network for it. I have real concerns about running the country with large numbers of distributed power. You know, electricity, photovoltaic and wind, they take up a lot of real estate. And the whole power grid would need to be redesigned. And then there's that big storage issue. So my viewpoint is I'd rather keep on producing hundreds of megawatts to gigawatts in central locations and using the existing distribution to move it around. But that's one man's view.
Can the existing, distribution network cope with 2.5 times to 3 times increase in power?
We got a real problem. Okay, I'm going to go. I'm not a policy guy, but the infrastructure for the U.S. electrical grid is a nightmare. And whatever we do, just the current grid, I'm going to go off on a tangent for which I apologize. It's laudable that folks want to electrify the transportation sector. Has to happen. If you take a look at how we generate CO2, about a third of it comes from the electricity sector, about a third of it comes from the transportation sector, and about a third of it comes from everything else. So if you really want to get to net zero, you really do have to electrify the transportation sector. By the way, that includes trucks, not just cars. Okay. What people don't think about is how are you going to make all that electricity, right? I mean, it's like folks have just not even thought about that. And if you run your electric vehicle with fossil fuel produced electricity, all you've done is you've moved your emissions from your tailpipe to the smokestack on the generating plant. So it worries me that people haven't really thought that one through, but you're correct. We're going to have to triple the generation. We're also going to have to figure out how to get it from where we make it to where we use it. It's a massive infrastructure problem.
Are there, when you help us understand the difference between getting a sustained fusion reaction in one of these big reactors and getting one in one of the small reactors, is it easier to do it in a small reactor, or do you basically have all of the same problem?
Maybe you should be given this pitch.
I'm reading the question.
You're asking the answer is there are multiple viewpoints. The guys working on small reactors say, we can make small reactors faster and more effectively than you guys making big reactors. I will say this, the biggest reactors are probably not a good idea commercially. And this is another long story. One of the problems you have, if you have a design process that can take years, let's take a look at ITER. ITER actually got started in like 1980. So they're designing with the best tools they have at the time around the best materials they have at the time. By the time they build the thing, it's completely out of date. Excuse me. And this is one of the areas where the little companies are much more innovative. They can take the risk of designing against a projected technology trajectory. And that's one of the things that's happening. And this does go to the big, small. There are folks who are looking at making small reactors with very, very powerful magnets, high temperature superconductors. If you look at the price of high temperature superconducting materials now, there's no way this is cost effective. But their argument is by the time we need it, it will be. So they can take the risk of designing a device that will be built with materials that don't yet exist economically, because they can assume that they will by the time they need them. And I think that is, this goes, now I'm really rambling on you, but it's part of why does everything cost so much and take so long? Excessive conservatism is a big piece of it. If you want to be absolutely sure that everything you've designed is absolutely for sure going to be there when you need it, be the right price, have the right structural characteristics. If you've ever worked a major government development program, you know that you can end up designing the same part 6 times just to be sure you got it right. And that adds a lot of development time.
There's a question about what kind of cooperation, collaboration exists between the Stellar Energy Foundation and the private venture companies that are interested in funding fusion.
Okay, so we actually, Stellar Energy Foundation is actually 3 partners. It's myself, a fellow named Jesse True, who's a fellow Princeton physics PhD and venture capitalist in the biotech area based in Princeton, and a fellow named Peter Burnham, who's a good friend and came out of the financial sector. And for about 2 years, we actually provided essentially free management consulting advice to a number of the young companies, helping them look at their business plans, introducing them to potential investors. Right now, our relationship to the companies is largely friendly. We have done one deal where, as I mentioned this, we made a grant to a private company that are actually experts on permanent magnets. And the grant we gave them helped them deal with the onerous cost sharing requirements of government contract. So we facilitated a contract between ARPA-E and the Department of Energy that funded work at the Princeton Plasma Physics Lab and Sabre LLC. We've made a grant to the private company, which allows them to then participate at the appropriate level. And we're looking to do more stuff like that, but not so much on the commercialization side. We're not an investor, all right? Our objective is to facilitate valuable work that everybody needs, that nobody's willing to pay for. It's kind of, if my lecture is, venture capital is private money in the private interest. Government money is public money in the public interest. Philanthropic money is private money in the public interest. And that's where we try to put ourselves. So, you can think about, for example, the project we're helping fund now at the labs is looking at the application of a new kind of magnet using modern permanent magnets to do field shaping where no one's done this before. If this works, there are going to be a lot of people who benefit from it because it's a whole new design dimension that's available to the industry at large. So we're not likely to put money into one company to try to help them out, but we might put a little bit of money into one company if what they're doing will help everybody out.
Okay, thank you. Can you say a little bit more about the gazintas and the gazautas? That is, what really is the fuel? Is that readily available? Do you have to put this thing next to the ocean? So tell us about how you get the fuel, assuming you react. But then also tell us when you're done, what's left over. You said that there were much less radioactive byproducts, but
less but not
you didn't
none.
say zero. Yeah.
Less but not none. Right. I'm not going to lie to you. So let's talk about the fuel cycle. There are actually more than one approach to doing this. I'll talk about deuterium, tritium, because that's the one that people have actually gotten energy out. Actually, the Princeton labs 25 years ago got 10 megawatts of power out of a thing called TFTR. It's the highest energy at the time. So that's a deuterium tritium fuel cycle. There are others, but I'll talk about DT because that's what most people are working on. Deuterium is easy to find. It's in seawater. There are lots of methods for separating it. It is not hard to get deuterium. Tritium is another story. Tritium is, in fact, a short half-life nuclear isotope. It needs to be handled carefully. There are radiation hazard issues associated with it, but nothing like what you have with the uranium fuel cycle. But there isn't an awful lot of tritium on the planet. So the approach that's taken right now is that you take a little bit of the tritium that you've got, which gets produced by CANDU nuclear reactors in Canada, more than you wanted to know. And once you've got your fuel cycle running, once you've got your fusion reactor running, the neutrons that come out of the reaction interact with lithium, which is contained in the blanket material surrounding the reactor, to breed more tritium. So the analogy, you know how people have talked about fission breeder reactors? You can actually breed tritium. So once you've got this thing going, if you've got lithium in the walls, and lithium is very plentiful, once it's going, you never run out. But you do definitely need some tritium to prime the pump. And there isn't an awful lot of tritium in the world right now.
Okay.
I guess it was the radiation issue. Okay, let me go on to the rest. I'm sorry. Okay, so there are 2 or 3 radiation safety issues. One of the big issues coming up is actually going to be, how is all this stuff regulated? The first one is tritium management itself. Tritium is indeed a radiation hazard, but it's a light gas and it disperses readily, and people know how to handle it. It ain't cheap, but people know how to handle it. And it really isn't anything like the danger of the byproducts that come from fission reactors. Next, the ash, what's left after you burn is helium, which is no problem at all. You're not left with depleted uranium, strontium, calcium, strontium 90. You don't have any of that stuff. So you don't have this massive radioactive waste to deal with. But you do have the issue of neutron irradiation of the surrounding structure. Okay, you're generating all these high energy neutrons. Some of them are getting absorbed in your blanket, converted into heat, making steam, running electricity. But every once in a while, neutron's going to bang into something structural and cause harm. It's a genuine concern. It's a concern for any nuclear process. The approach here is to use materials that are known to be radiation resistant. There's certain kinds of steels and certain kinds of cements, but you really have to design for maintenance, because these reactors, when they run for a long time, will definitely need to be maintained. And one of the issues for designing a commercial reactor as opposed to a science project, when you're all done with it, you throw away, you go to Uncle Sam, you say, build me another one, right? But if you're in business, you can't do that. So one of the issues here is to use different design criteria to make these things more maintainable. And that is not a trivial task. It's real work. Not impossible. It's what I refer to as difficult but routine engineering. All right. You got to spend the time and the money to do it. But if you spend the time and the money, you'll be able to do it.
Okay. We're getting down to the end of the questions. There was a question.
Are we getting down to the end of the audience too?
No, it's still just about everybody is still on.
I commend you. I'm going to reach up here and see. My God.
So,
okay.
Are there intellectual property ownership considerations yet?
What do you think? Of course. The IP is always an issue. I would use the analogy, really, it's very interesting. In the past year, the global response to COVID has been an interesting model for what should be the global response to climate. If you take it seriously and you throw the energy and the attention against it that it needs, the scientists can accomplish miracles, but the society has a lot of other stuff to do. And the intellectual property is going to be a very significant issue because the private companies are not interested in sharing their insights, and the government has issues with paying companies to make stuff that they don't share. And it is not a trivial task. There are well-intentioned people on all three sides of that two-sided table trying to work it out.
Well, are there, given the lifespan of patents, are people filing for patents?
So again, there's a really complicated, if you talk, I'm going to go to a higher level of abstraction, if you'll forgive me. If you think about the space program, all right, nobody made money commercially flying people to the moon. But the Apollo program spurned from the collateral benefits a 50-year run of technology-driven prosperity. The same is likely to happen here. So there will be folks in the supply chain learning how to make high-temperature superconductors, okay? The fusion companies aren't making the high-temperature superconductors, the superconductor companies are. They will have patents of their own for how to produce these materials. They'll own the IP. But oh, by the way, every NMR machine on the planet is going to be better and different when they can start making them with high temperature superconductors as opposed to the current stuff that they're using. So the IP is going to be on the material science side for that one, not on the fusion reactor side. A lot of the analytical tools, you know, the very, very complex plasma physics and analysis stuff has applications beyond fusion reactors. So the collateral benefits, and oh, by the way, the benefit of having the ability for smart young people to have long-term rewarding technology-driven careers should not be underestimated. This is a domain where when it gets going, it's going to be very attractive. And you know, there will be young scientists who can make this their careers, which will be a good thing. They'll be generating, I know I didn't answer your patent question, but the answer is certainly patents are getting created. In some areas, the IP is really better as a question of know-how than patent, right? If you have some secret sauce, if you know how to cook a souffle, okay, the recipe is not what matters, it's the know-how. And the know-how, which is something secret that is included in institutionally, is often a more valuable piece of IP than a patent. Patents can be replicated, know-how can't without getting people. So, long answer.
Okay, you have a few more questions that have come in. What is the present state of ITR or ITER?
ITER. This is a very good question. It is actually moving along great guns. I suggest that the questioner go to the ITER website. They're actually starting to install. This is a massive construction project, by the way. The size of this thing is unimaginable. But they're putting the magnets in place. Some of them they've gotten started on the cryostat. They're actually on track to first plasma, I think, in a couple of years. But this was a project that had gotten very much off track and is back on track. It's an amazing program. Great science project. I don't know if it's going to actually help us commercialize anything anytime soon, but it's a major accomplishment, what's happening there.
In terms of the time frame, is it useful to think about, well, you mentioned the moon project. That seemed like a fairly difficult undertaking that was done in a relatively short period of time compared to fusion, not to mention the Manhattan Project. Is this something that could be greatly accelerated if you got the world's best physicists all collected together working on it and the world's best engineers? Or is this going to be like the IBM 360, the Mythical Man month? You add people to the project and it just takes longer.
So thank you for asking that question. My dad actually worked on the Manhattan Project. If the United States hadn't gotten involved in a world war in December of 1941, we'd still be working on our first fission reactor. It was a question of urgency. I mean, the entire Manhattan Project was really 3 years. I mean, people knew about the physics and the this, and there's the famous Einstein letter, but the reality is Oak Ridge got going in early 1942. And by July 1945, there was a working weapon. And in between, they had to do everything. So, if you really care, you can get it done. Let's take a look at the development of mRNA vaccines, right? Gee, we need them tomorrow because people are dying. Amazingly enough, we got them tomorrow. So the answer to your question is, if there were an appropriate sense of urgency and not enormous resources, this is not an Apollo program. I mean, at one time, this was before the Great Society, in early 64, 65, the peak of the NASA spending, it was 5% of the US GNP. It was a question of war. To develop commercial fusion, it's not a question of being on a wartime footing. But you can't just treat it like a science project. Things are getting better, but I think the funding level is about 1/10 of what it ought to be. And that's not a lot. That's like $10 billion a year instead of one.
There's a question about, are we America being excessively conservative vis-a-vis the Russians and Chinese? Is there a trade-off here between a willingness to take risk and the willingness to perhaps, or to ignoring the fact that you may provoke a disaster? So to what extent is there multinational cooperation here versus nationalistic competition?
It's a really good question. There's cooperation and competition. ITER is actually everybody cooperating. It's the EU, it's China, it's the US. ITER is a magnificent act of cooperation. Separately from that, and I don't really know what's going on in Russian fusion. They were the leaders a long time ago. I don't really know what they're doing now. The Chinese are both cooperating and competing. There are actually joint projects in China. There's a thing called EAST, where the US labs are cooperating with the Chinese labs, but there's also a lot of separate activity in China. And I would say China is a hard intelligence target. You don't really know everything that's happening there, but you do know that they've made it a national priority, that they really do understand the geopolitics of energy. And I'll go back a step. And there are exactly 2 countries in the world that are currently exporting significant numbers of fission reactors: Russia and China. So they are in the nuclear energy business as an export business. And the Chinese understand the importance, the geopolitical importance of the next generation of energy. I'm not sure we've gotten there yet.
Okay, well, I think we've gotten down to the bottom of the list of questions. I just say that it seems to me that whatever your definition of infrastructure is, this ought to be a part of it. So I guess we'll see. But Matt, I want to thank you very much. Oh, and let me just say, do you have any concluding remarks that you would like to make before we bring this?
Concluding remarks. First, I think it's just fantastic. As I said in the opening remarks, the Princeton class of 70 are among the best people I've ever known, and it's been a delight to be a brother-in-law. The alumni that I've dealt with generally are beyond magnificent, and again, thank you for all those introductions. And I'd say stay tuned, be involved. The climate issue is very real, and it isn't going to solve itself. And I'd say as responsible citizens, for me, this is chapter 4. I'm trying to do what I can to leave the world a better place than I found it. And the way I think I can do it is this. But, there are other paths. There are other paths. And I just say, do more than nothing.
All right, well, we'll leave it.
And I will add, if anybody wants my personal contact info, if they want to take a deeper dive or whatever, feel free to share it.
Okay, well, thank you for that. This has been recorded. I think we will make that recording available to those who couldn't join us tonight. And Mo, unless I've forgotten anything, I'm going to bring it to a close. I thank everyone for attending, and I'll see some of you on the air on Sunday night or Saturday night for the wine tasting. So.
Well, yeah, well, goodbye, and thank you for everything. George, did you want to say a few words?
No, I would just again thank Matt for this wonderful presentation. I think we went just about an hour and a half, and
Wow.
there were lots of really searching questions. I don't know how many we had online, but it was a good representation. So this was another, I think, major step in your educating the Princeton community, Matt. And
the Princeton community is worth educating. So thank you very much. It's really
so
been.
the university thinks.
Yeah. And thanks, Matt. Say hi to May, okay?
I will. She.
All right.
We need to get together in real life.
We will soon.
This is just getting to be difficult. Mo, thank you very much.
Thank you.
This worked out extremely well.
Okay,
And
well,
it's just a pleasure. I love dealing with people who care. That's what it comes down to. Thanks.
we'll see each other soon.
All right, thank you, everyone.
I sincerely hope so.
Bye.
Thanks again.
All righty. Bye-bye.
George, Mo, everyone, see ya.
Bye, everybody. You guys can leave first. I don't want to shut the door in your face. Okay. Bye.
I'm gone.
Bye.